Continue this series on p-adic geometry, and the topic I want to discuss today on Thursday is vector bundles on the FarguesFontaine curve and Banach-Kolmé spaces. And more precisely, I would be especially interested in the interplay between these two types of objects. So we will see that vector bundles on the FarguesFontaine curve give rise to interesting geometric objects, which are called Banach-Kolmé spaces. And conversely, we will see how the geometric property of these objects help us to understand vector bundles on this funny curve. So maybe I can start by giving like some references for what I'm going to do in these two lectures is to basically I'm explaining a part of chapter 2 of this big paper of Fargue and Scholze. And so this chapter 2 is in substance like preliminary material for what they do in the rest of the paper, which is about how to use the FarguesFontaine curve and ideas from geometric Langlands to study, to say something about the local Langlands correspondence. Which of course goes far beyond what I'm going to discuss. But I can also mention another paper by Fargue, at least if you can read mathematical French, which is called Simple connexité des fibres d'un morphisme d'Abel-Jacobi et théorie du corps de classe locale. So in this paper, Fargue somehow explains the GL1 case of what Fargue should do in this paper. And that's a nice application of all the technology I'm going to discuss in these lectures. Okay, so let's start by recalling where we stopped in Judith's lecture. So let E yeah, but I'm not really going to discuss it anymore. Really, everything I'm going to do today is like part of this.
So maybe so that those at home can hear it, Peter Scholze mentioned that we should also mention as a reference Arthur-César le Bras thesis on that topic.
Okay. So let E be a finite extension of QP. And let's fix a uniformizer pi, and let FQ be the residue field of E. And let also S be a perfectoid space in characteristic P living over FQ. And to the datum of E and S, what we saw in the last talk is that we can attach YS and XS, which are both analytic adic spaces over SPA E. So, I mean, these objects really depend on E, but to keep the notation light, I will just, E is fixed once and for all, and so I will just remove them from the notation. And so if S is affinoid perfectoid, then this is defined as we saw. So YS is defined as the adic spectrum of ramified Witt vectors of R plus. And so this is an affinoid adic space, and you remove the locus where both pi and Teichmüller of var pi vanish, where var pi is some pseudo-uniformizer of R. And on this, you have a Frobenius action by S, and the curve is defined as the quotient of YS by this Frobenius action. And in general, you have to glue these constructions, which are done in the affinoid case, to get the FarguesFontaine curve for any perfectoid space over FQ. So maybe before getting to vector bundles on this curve, I should maybe first stress something which is important, which is the fact that ys and xs are, as I wrote, analytic adic spaces over spa E, but they don't live over S. So there is no morphism of adic spaces. Yes, try from XS to S. So if you know about the Fargues-Fontaine curve as originally defined by Fargues and Fontaine, you can, in first approximation, imagine that this version for any perfectoid space S is some kind of family of Fargues-Fontaine curves indexed by the points of S. But you should keep in mind this caveat. And in fact, however, there is somehow a way to think of XS as living over S. And for this, let me also recall something that you did mention, which is that, well, we know that we have this nice diamond product formula for the diamond of YS. And so we know that at the level of diamonds, you have a map from YS diamond to S. And sections of this map, they really are in bijection with untilts. S sharp of S which live over E. And whenever I give myself such an untilt, any such untilt in characteristic 0, gives rise to a Cartier divisor. On YS. And in fact, you can also further map this down to XS. And this way you get a Cartier divisor on XS, which is, well, as we saw, we have this theta map from the Witt vectors to the ring of integrals element of the untilt. And the kernel of this theta map is principal generated by a non-zero divisor. And this gives rise to the ideal shift corresponding to this Cartier divisor. And so if I denote by div1, so let me introduce div1 to be the moduli space of Cartier divisors on the Fargues-Fontaine curve. Arising in this way, so coming from an untilt over E. Well, then we see that, I mean, somehow by construction, div1 will be isomorphic to the following object. So a map to spa DE is the same by definition of the diamond as giving ourselves an untilt. And then this composition actually only depends on, I mean, factors through the quotient by Frobenius. Where here the Frobenius is just the Frobenius of this diamond, which is a functor on a category of spaces in characteristic P, so it has a natural Frobenius. So concretely, it just acts by an untilt is a perfectoid space over E together with an isomorphism of the tilt with the given perfectoid space. And you can always just compose this isomorphism with the Frobenius. And this is, so this one, no, so this diamond has a very nice property. So div1, yeah. So the map from div1 to the point, which is just like, if you want just, I mean, the notation I will use for the final object, spa D of Q, which is like just a V shift. this is as nice as possible. So this is proper and smooth in some sense. So in this world of diamonds, you can make sense of being proper and of being cohomologically smooth. And this object has these two properties. But note that it's not the same thing as the Fargues-Fontaine curve. So this is in contrast with what happens for curves, like usual curves in algebraic geometry. If you look at, okay, maybe I give a name to this kind of divisor. I will a name which I will try to justify later. I will call this Cartier divisors of degree 1. And in usual algebraic geometry, moduli space of Cartier divisors of degree 1 would just be isomorphic to the curve itself. But now we get a diamond which does not identify with the diamond of the Fargues-Fontaine curve. However, what you can still observe is that whenever you pick, so maybe I move to. So the difference between the two is just a difference about which Frobenius you are using. So if S is, again, a perfectoid space over FQ, then div1S, which is, by definition, the product of div1 with S, is, by the formula I gave, just spa dE times S, where you mod out by the Frobenius of spa dE times the identity. But if instead you look at the Fargues-Fontaine curve, or rather at its associated diamond, then by this product formula that you did explain, you get that this is the same as the same product, but where you mod out by the Frobenius on S. So concretely, like the two Frobenius are acting differently on the moduli problem. For this one, you just somehow compose the isomorphism of the tilt with Frobenius, and for this one, you just compose the map to S with the Frobenius of S. And so these two objects are not the same, but still the product of these two Frobenius. Sorry, I should write the other way around. Identity times Frobenius of S. And so this product would just be the Frobenius of this diamond spa d times S. So on the underlying topological space, it just acts as the identity. And actually, even on the étal side. And so in particular, you get at least an identification of the underlying topological space of this diamond, div1S, and the underlying topological space of the diamond of XS, which is the same as the underlying topological space of the Fargues-Fontaine curve. So at least at the level of topological space, because you had this map from div1 to the point, you do get a map from the underlying topological space of the curve to S, which somewhat gives some more precise justification for this heuristic that the Fargues-Fontaine curve is some family of like usual Fargues-Fontaine curves parameterized by S. And because the map before was proper and smooth, this map is open and closed. Okay, let me, yeah. Look, by definition of the diamond of spa E, it parameterizes untilt of S, which live over E. And here I'm just modding out by Frobenius, because what I do is I'm not looking just as Cartier divisor on YS, but on I look at this composition from S sharp to XS. So I just mod out by, like, the Frobenius is not doing anything. Okay, so let me maybe just make one last remark about this div1. I mean, it will reappear a bit later today, which is that, as I said, the map from div1 to the point is as nice as possible. In particular, this map is QCQS, so it's because it's proper. So in particular, it's quasi-separated. But div1 itself is not quasi-separated. So saying that div1 is quasi-separated would just mean that if you take two quasi-compact objects living over div1 and you form the fiber product over div1, it would stay quasi-compact. But it's visibly not the case because SPA-DE is a spatial diamond, so in particular it's quasi-compact. And if I form the fiber product of SPA-DE with itself over div1, I just get Z many copies of SPA-E. So I get something which is not quasi-compact anymore. So this is something which happens quite often in this world of diamonds, that this final object here, it's really just the final object of the topos of V or Pro et al. Sheaves, but it's not itself, SPA-DFP is not itself a diamond or a perfectoid space. Because FQ is perfect, but it's not a Tate tree. It has no pseudo-uniformizer. Okay, so now let me actually come to vector bundles. So that was just somehow to say a little bit more about these relative FarguesFontaine curves. So the key construction regarding vector bundle is due to FarguesFontaine. So I will denote by K the algebraic closure of FQ. And by E breve, the completion of the maximal and ramified extension of E, which is the same as fraction field of ramified with vectors of K. Let me maybe make one last comment about the FarguesFontaine curve, because before I forget, that all the story also makes sense if E is a local field of positive characteristics. So if E is of the form FQ double parenthesis pi for some abstract variable pi. You just have, I mean, the story is even simpler because then you just replace ramified with vectors by of R plus, just get replaced by the ring of formal power series in the variable pi over R plus. And so in this case, actually, like all the objects are more concrete, but in these two lectures, I will just focus on the case of p-adic fields. Okay, and so the observation is that we have a tensor exact functor from like for any perfectoid space S over K from the category of isocrystals over K to the category of vector bundles on the FarguesFontaine curve associated to S and E. So this is the category of isocrystals over K. So by definition, this is the category of an isocrystal is just a finite dimensional E breve vector space plus six. Yeah. So maybe I call it D plus a sigma semi-linear automorphism of D, where sigma is the Frobenius on the Witt vectors. And how does the construction work? Well, if you have such an object, so just a pair D comma phi, what you can do is you just map it to the vector bundle on the Fargue-Fontaine curve. So you use the fact that the Fargue-Fontaine curve, the p-adic Fargue-Fontaine curve, is defined by some kind of uniformization from YS. And so the corresponding vector bundle, E d phi, is just what you get by descending the trivial vector bundle D times OYS using the diagonal phi action. Maybe this Frobenius, I call it phi D. Well, it's, I mean, a vector bundle on the Fargue-Fontaine curve will, by construction of the Fargue-Fontaine curve, be the same as a phi equivalent vector bundle on YS. So as a vector bundle on YS is trivial of dimension given by the rank of D, by the dimension of D. And then I use this Frobenius structure. So why is it nice? Well, for two reasons. Like, first of all, it gives us a way to construct many vector bundles on the Fargue-Fontaine curve. But also, we understand very well this category. So by the Dieudonné-Manin theorem, we know that the category either K is an abelian semi-simple category. So any object is of this category is a finite direct sum of simple objects. And the simple objects, we know what they look like. So they are parameterized by rational numbers. And so for each lambda in Q, I can consider the following isocrystal. So let me write lambda as D over R, with D on R being co-prime and R being positive. And then what I do is, so it's just as a E-breve vector space, it's dimension R. And so this matrix of Frobenius is given by the following expression. So one below the diagonal and pi to the D on the top right and true. Yeah, I mean, there is, I mean, I don't want to say anything about Stuka, so maybe it's better to discuss this afterwards. I mean, yeah, isocrystals can be seen as some kind of Stukas, but I don't want to really go into this. So, right, so this category is quite explicit, and as one piece of notation, in what follows, we will denote by, so again, if lambda is in Q, we will denote by O lambda the image of, well, not of this isocrystal of slope lambda, but rather there is a change of sign. So what we get by applying this functor to as a crystal corresponding to the slope minus lambda. No, it's very far from being fully faithful, even over a geometric point. So I will come to this later. Okay, so next thing, so that's a construction giving us many vector bundles on the FarguesFontaine curve. Next thing I would like to discuss is I would like to say something about cohomology of vector bundles. So I will come back to the properties of this construction of FarguesFontaine a bit later, maybe today and more likely on Thursday. But for this, we will need first to have some understanding of the cohomology of the vector bundles we get in this way. So before discussing these specific examples, let me start by a general remark that if we look at cohomology of vector bundles on the FarguesFontaine curve, at least when S is affinoid perfectoid, we only get something in degrees 0 and 1. So if S is affinoid perfectoid over FQ, then this space Y S is, I mean, it can be written as a union of adic spaces YSI, where I is some interval like goes along all possible intervals in 0 infinity. Sorry. So it's a compact interval with rational ends. So A and B are both rational numbers. And well, what is this YSI? It's just the locus in YSI where the absolute value of, so it's a space of valuation by construction of adic spaces. And we look at the locus where the valuation of Teichmüller of pseudo-uniformizer is in between valuation of pi to the b and valuation of pi to the a. And so this is an increasing union, which is countable, because it's just, I mean, I can restrict myself to intervals with rational ends. And each of these YSI is, well, first of all, it's affinoid, but then it's also very close to being perfectoid. It's a terminology that you did mention. It's a superfectoid, meaning that it becomes perfectoid after base change from E to the perfectoid extension you get by adding all possible piece power of the uniformizer pi and taking the p-adic completion. And the map from E to this perfectoid field splits as a map of topological vector spaces. So that's a convenient trick that when you have some control after base change to this perfectoid field, you can actually deduce some result over E itself. And so in particular, what you can deduce from this fact on almost purity is that for any vector bundle on say YSI, then it has no higher cohomology. Right. Well, I'm confused. I think actually I don't even need this fact. Just the fact that it is affinoid should be enough. So for I positive. And say again? Right. Okay. But I use this superfactoid property to check shiftiness. Say again? Yeah. So the only need you are using is that this adic space YSI is Schiffy and affinoid. And when you look at functions on, if you take I, which is included in I prime, and you look at the induced map of functions, restriction from function on YSI prime to YSI, you also know that this restriction map has a dense image. So by some version of topological version of Mittag-Leffler, you deduce that same is true if E is a vector bundle on all of YS. And okay, maybe I can write there. So in particular, you deduce the useful fact that still under the assumption that S is affinoid perfectoid, the cohomology of, so if no E is a vector bundle, on the Fargues-Fontaine curve, seen as a phi equivalent vector bundle on YS, its cohomology is just computing by the following two-term complex. Where the map is given by Frobenius minus identity. So you only have H0 and H1. H0 is given by phi invariant global sections on Y, and H1 is given by the co-kernel of Frobenius minus identity. And this is true for any vector bundle. But now I want to discuss in more detail what happens for the vector bundles coming from isocrystals. Yeah, that's what I just said orally, but did not write that. This is some kind of Stein space. So when you look at the like you have some increasing union, when you look at the corresponding restriction maps on function, they actually have dense image. So you can use some version of Mittag-Leffler in the topological setting to ensure that you have no R1 limb. So next. As I said, we would like to understand cohomology of vector bundles coming from isocrystals. And before stating the proposition, let me start by one example, which is somehow the key example. So let's look at the case of the line bundle O of 1. So let me, when I say understand cohomology in this particular case, it means that I would like to understand the following functor, denoted BCO of 1. So it sends S in perfectoid space over FQ to the global sections on XS of this line bundle O of 1. And there is a nice description of this functor, which involves Lubin-Tate theory. So I will try to explain it, I mean, in a rather sketchy way, but at least I try to give the statement. So it goes as follows. So we let G be Lubin-Tate formal group law for OE. So if E is QP, which I mean you can certainly just restrict to this case if you like. This is just given by the multiplicative group. What we know is we can, the formal. So we can pick a coordinate. So it's a one-dimensional formal group of height 1 with an action of OE. And we can choose a coordinate in such a way that, so an isomorphism of G with a formal spectrum of ring of formal power series in one variable X over OE, in such a way that the logarithm of G, so any such formal group law when you base change from OE to E, so when you go to characteristic 0, it becomes isomorphic to GA. And this isomorphism is given by the logarithm of your formal group law. And in this case, you can pick this coordinate in such a way that log G, which goes from GE to GA of E, is just given by the following formula. So X goes to X plus 1 over P XQ plus 1 over P2 XQ cubed, XQ square, and so on. So I don't want to work with G directly, but rather I want to form its universal cover. So in the category of group objects in formal schemes. So G tilde will be by definition the inverse limit over multiplication by pi, which is an element of OE of G. And this can be seen basically because if you reduce mod pi, the action of, maybe I should write this way, the action of this element pi is given by x to the q by definition of a Lubin-Tate formal group law. So this is just the same as a formal spectrum of a power series ring, but now in a perfectoid variable, which I will call x tilde, 1 over x infinity. Okay, and now I want to make the following claim. Then, right. So the claim is the following. Let me take S affinoid perfectoid again over FQ. And let's pick sum and tilt. S sharp. Which leaves over E. Then the claim is that the map sending X to the sum over Z of pi I X to the Q minus I induces an isomorphism between G tilde evaluated on the OE algebra given by the plus ring of R sharp. So what is this? Because of this identification of G tilde, you see that, I mean, this will be identified with the inverse limit over Frobenius of R of the R points of formal spectrum of OE double bracket X. Sorry, yeah, of R plus points of this, which are just given by the topologically nilpotent element in R. And sorry, this is R sharp. But no, this is also the same by definition of the tilt. This is the same as topologically nilpotent element in the tilt of R sharp, which is R. So my element X, which belongs to here, I can see it as a topologically nilpotent element in R. And so in particular, I can take its, which is a perfect ring of characteristic P. So I can certainly take such Q's power roots and then form the Teichmüller element to get an element which a priori lives in the Witt vector. But I claim that this is in fact living in the evaluation of this functor BC of O1 on S, which, well, just by definition of this functor, it's given by H naught YS of the structure sheaf, and then phi, the eigenspace where phi is given by multiplication by pi. Okay, so these elements belong to the Witt vectors of R plus, ramified Witt vectors, and so I can certainly see this element as a global section of the structure sheaf on YS, and then it's not hard to see that it satisfies this equation when Frobenius is acting. And the claim is that this is actually defined a bijection.
They require any partial simplification, right? To say that.
Yeah, sure. Yeah, but no, I want to stay the. Okay, I wanted to say the thing about the logarithm. And then I'm not like done. Okay, so in such a way that the evaluation at S sharp map from BC of O1S to just H naught of the structure sheaf on S sharp, which is just R sharp, identifies with the composition from G tilde R sharp plus to, well, maybe, yeah, maybe I should say like this, generic fiber. Going to R sharp. And I mean, this is just the projection to the first component, and this is this logarithm map. Okay, so let me maybe, I don't have much time left, so let me maybe go a little bit quicker and just mention what you can deduce from this. So from this you can, well, already one thing that you see is that as a functor on perfect weight spaces over FQ, BC of O1 is represented by, I mean, it's just given by the V sheaf associated to FQ X 1 over P infinity. Right? Because what we claim is that BCO1 of S is just given by when S is par R plus, is just given by topologically nilpotent element in R. So this space, I mean, you have to be careful that this is not a perfectoid space. Again, because it's not analytic, it does become perfectoid, however, after you remove zero, so to say. And it also has an interesting feature, which I just want to note in passing, that some of the opposite phenomenon to what we saw for div1. So this is certainly, I mean, this one is quasi-compact, but the map from BC of O1 to the point is not quasi-compact. Because after you base changes to the, say, the adic spectrum of a perfectoid field in characteristic P, the space you get is the open perfectoid open unit disk, which is not affinoid. So that's one first consequence. We see that this functor is actually a V sheaf represented by this object. And something else you can deduce from this is that you have, for any untilt, S sharp of S, you get a short exact sequence of vector bundles zero goes to the structure sheaf on the FarguesFontaine curve, goes to O1, goes to the skyscraper sheaf supported along the corresponding closed Cartier divisor defined by S sharp, goes to 0. So, I mean, getting this out of this identification requires a bit more work, but I don't really want to go into this. I should also say here that this functor here we have on the left, it's a functor on perfectoid spaces of characteristic P, taking value by construction in the category of E vector spaces. But in this isomorphism, we somehow lose the E-linear structure. So a better way to write this is to identify this with the diamond of the perfectoid fields that you get by looking at E infinity, which is the completion of the Lubin-Tate extension of E, which is the extension you get by adding all P to the n torsion when n varies elements to E. So this is a perfect field, perfectoid field, sorry. And oh yes, yeah, thank you. And so the Galois actions, the Galois group of E infinity over E identifies with OE cross. And the OE cross action you get there corresponds to the OE cross action you have there. And the action of pi would correspond to the Frobenius on this diamond. So as a small remark here is that in this way, you can also see an alternative description of this diamond div1. Which is that div1 identifies with, well, so recall that this is SPA DE modulo Frobenius, But this I can also rewrite as spa dE modulo, sorry, spa dE infinity modulo Frobenius on the action of OE cross, which is the Galois group of E infinity over E, as I said. And because of this identification, which is compatible with all the actions, you see that this is also the same as BCO1, where you remove 0, divided by the action, the natural action of E cross on this sheaf of E vector spaces. So that's another way to think about this diamond div1, which gives some kind of partial justification for the terminology I introduced before, because you can think to this as, I mean, if you believe me that at least pro eta locally the only line bundle of the FarguesFontaine curve of degree 1 is given by O of 1, you see that what this diamond on the right parameterizes is exactly the datum of a section of a line bundle of degree 1, which is non-zero fiber-wise. So it's some kind of like what a usual Cartier divisor of degree 1 would be. And so these kind of identifications play a big role in this paper of Fargues that I mentioned at the beginning. Okay, so maybe now let me state the main proposition about cohomology of vector bundles coming from isocrystals. And say something about the proof, maybe. One last thing I should mention is that it's a very interesting and very amusing exercise to try to, let's say when E is QP, and so our formal group law is just formal GM. It's quite interesting to see how these identifications of diamond do at the level of geometric points. So it's a nice way to parameterize primitive elements of degree 1 in terms of elements of non-zero elements in the maximal ideal of your perfect weight field, which uses Lubin-Tate theory for general E. Okay, so here is the proposition. Yeah, maybe let me come back to it after. I really want to state this proposition before stopping. So let's pick lambda a rational number. So the proposition has several parts. So first we will look at the case where lambda is positive. Then the claim is that the cohomology of O lambda in degree 1 vanishes when S is affinoid perfectoid. So the only interesting things that can happen should be in degree 0. And again, I will use the same notation as before. So in this case, I claim that the projection from BC of O lambda, which by definition will be the functor on perf FQ, sending S to H0 XS O lambda. So projection from this functor to the point sorry. So this is a vanishing statement for H1, and no, I'm speaking about H now. To the point is representable in locally spatial diamond. And partially proper. And it is also even cohomologically smooth in this case, if you know what that means. So we already saw that in the case where lambda is 1, BC of O1, I said, is, well, somehow is quite explicit, but this object we have on top is not a perfect-weight space. It's not even a diamond, but it at least becomes so after any base change to a perfect-weight space, or even to a diamond. So this property over here, it means that whenever I base change to a locally spatial diamond, the map from BC O lambda to the point, I do get a locally spatial diamond. And partially proper is, roughly speaking, proper without the quasi-compact assumption. So it means that you satisfy, well, first the map is quasi-separated, and then it satisfies some form of the valuative criteria. Okay, and there is a small bonus when the slope lambda is still assumed to be positive, but smaller than the degree of E over QP, then it's even more explicit. So then, exactly as for O of 1, there is an isomorphism between BC of O lambda and p-adic FQ X d1 over p infinity, where d is, I write as before, lambda as d over r, with d and r being coprime. So the case of lambda being 0 is almost the same, but there is a
One thing to the principles about vector models curves, right? You usually look at vector model curve and you look at the part of those vector model. So it's not generically a vector model on the base split. But these things are not about vector models. They still have some different structure. They're not about.
right. So if lambda is 0, then, well, you know that in this case, it's again quite explicit. So you have an isomorphism natural map from E underline to the Banach column like BC of O, which is defined exactly as I did for O lambda for positive lambda. And this is an isomorphism. And for H1 of O, it's not anymore true that it vanishes on any affinoid perfectoid, but at least this functor will vanish after pro-étale simplification. So even if S is affinoid perfectoid, it's not necessarily true that this H1 vanishes, but you can find a pro-étale cover of S such that this becomes true. So in other words, the simplification of this functor is just 0. So again, the only interesting happening is in degree 0, and then we just get E underline, which I recall is the functor sending S to a continuous function on S, on the underlying topological space of S to E with its natural p-adic topology. Okay, and let me just state the last point, which is a case where lambda is negative, then the opposite situation happens. So then we know that H0 vanishes for any perfectoid space S. Here. And once again, so now I will use a different notation in this case. I claim that the projection from BCO lambda, which is now defined to be the functor sending S to H1 XS or XS lambda to the point is, as before, as in point 1, is representable in locally spatial diamonds and partially proper. And it's also smooth, exactly as in case 1. Okay, so the behavior is quite different depending whether you are like non-negative or negative slope. So maybe let me just take 1 more minute just to give one example. So basically the proof is by, I mean, some arguments involve some explicit computations, but then most of the argument is some kind of dévissage from the case of BCO1 and using this short exact sequence. So for example, this short exact sequence, you can twist it by O-1 to get a short exact sequence like this. And you can look at the corresponding long exact sequence in cohomology. And I already described for you in this example in point 3, what the shifts, what the cohomology look like for the structure shift on, okay, sorry, that's all I need. So for the structure shift, we know we only get E underline. And for this one, what we get is just the diamond of the affine line over S sharp, because the global sections of this are just in degree 0 given by global sections of S sharp. So what we get is that the Barnard-Kolmes space of O minus 1 is, so this is like for any S, is given by the quotient of A1 S sharp diamond by E underline. After base change to S, yes, thank you. So yeah, whenever I pick a perfectoid space together with an untilt, I can give this presentation of this Barnard-Kolmes space using this short exact sequence. But this looks like a very strange object, but this is still a reasonable diamond. So in particular, it has these properties, and it's even cohomologically smooth in some sense. Okay, sorry for going over time. I should stop here.